Hello and welcome back to Calculus 1, the last section of chapter 4 on antiderivatives. And these antiderivatives are also known as integrals. And I will already tell you, you know all of these formulas if you know derivatives, because you just read the formulas backwards. For instance, if the derivative of tangent is secant squared, then the integral of secant squared is tangent. So, and that's the end of the story. So every single formula for derivative you learned so far, if you read that formula backwards, you are talking integration. And now we need to learn notation and a whole bunch of other stuff that it's important about it to just close the chapter. So first of all, is antiderivatives are backwards derivatives, and we are going to take a look at some stuff. So let's go first and say the derivative of x squared is 2x, which means that the integral of 2x dx is equal to x squared. Now there is also something that goes plus c, but I'll have to make the argument for it and add it, so leave some space there. So it's not complete yet. Now this is your notation. Both of these must be present, so integral sign and dx both must be present for the correct notation. Alright, so if we take the derivative of x squared, we get 2x, and now we say the integral of 2x is equal to x squared. So we go backwards. But here is the issue and why we need to do something better there. If I have x squared plus 100, what's the derivative? 2x. So you see how this derivative literally obliterates this constant, right? And now, if I take the integral of 2x dx, I'm still going to get x squared, right? So there is no way for us, without additional information, there is no way for us to retrieve plus 100. Even if I go and I say d dx of x squared minus 7, it's still going to be 2x, and the integral will still be integral of 2x dx is equal to x squared. No way for us to retrieve minus 7 plus 100 or a 0 on the first one, which is why we always put this plus c. Okay? So plus c is for an unknown constant, and in some cases we will be able to compute that value. We'll need something called initial point and so on, so we'll deal with that next class. Today we are learning notation, so you must have integral, you must have dx to say I'm taking integration in respect to x. We'll see more importance of this dx later in chapter 5. Today we are learning that you have to put both of these, and once you are done with integration, you have to put plus c. Now, plus c takes away a point if you don't do it on a test, but it takes more than that in differential equations. So you need to get used to immediately put a plus c at the end.
Do you have to do that for the first one? Plus c?
Yes, because your problem looks like this. Integral of blah dx equals, and now you're going to get something here. You immediately put plus c because you don't know what happened, right? You never have the stuff on the left, right? You don't have the stuff on the left. So you always put plus c. Sometimes that c is 0, sometimes it's not a 0, so it depends. All right, so now we understand notation, hopefully, we understand that this squiggly line and dx, they're a pair, right? And you're going to squeeze the function in between, and then you will have x squared and so on. So now let's take a look at the important antiderivatives, also known as integrals. So where do we start? Well, the derivative of constant was 0, right? So the integral of 0 dx is going to be 0 plus constant c, which is just a constant c. The best thing over here is anytime you want to check your integral, you just differentiate, and you better get what was inside the integral, which we call integrand. All right? The integral of a constant k dx is going to be kx plus c. So let's say integral of 7 is 7x, because the derivative of 7x is 7, to go back, right? So if you differentiate this, derivative of x is just going to be 1, so you just get k, which is what we had there. Now here is the formula that it's different than what you're used to. Integral of x to the n dx. And this one is x to the n plus 1 over n plus 1 plus c. Now, this particular formula is going to take care of, again, just like derivatives, 3 different types of functions. You can have x to the 6, which is a polynomial. You can have the cube root of x, which is x to the 1/3, which is what we call a radical function. And then you can have 1 over x to the x squared, let's say, which is x to the minus 2. So 3 different types of functions covered in one formula, just like in the derivative. And you will always use the same n plus 1. So 6 plus 1 is 7, 1/3 plus 1 is 4/3, negative 2 plus 1 is going to be negative 1. So if I have the integral of x to the 6 dx, the answer is x to the 7 over 7 plus c. Because all I did is my n was 6, so 6 plus 1, right? 6 plus 1 is 7. If I had the problem below of integral of cube root of x dx, I rewrite that as the integral x to the 1/3 dx, and now it becomes integral of x to the 4/3 divided by 4/3 plus c, because I have to do plus 1 on whatever the exponent is. If the exponent is 1/3, 1/3 plus 1 is 4/3. And finally, the third example that I gave over here was 1 over, generally they like to write it as dx over x squared. So I don't want you to confuse that. That dx is actually multiplied into the function. You can't drop dx ever. I just graded Calc 2 exams, and 2 or 3 students lost points on the notation for not placing down dx's, which is terrible in Calc 2. So we have integral of x squared, x to the negative 2 dx, and that's going to be x to the minus 1 over minus 1 plus c. You can simplify that as minus 1 over x plus c, right? You can make it better through algebra. But the idea is that you have polynomial function, radical function, and the rational function all taken care by the same formula. What do we have? 5 minutes. So we have integral of e to the x dx is equal to e to the x plus c. That's, the one that goes back and forth like that. And I'm just going to put a modified version here with a. E to the ax dx is going to be e to the x over a plus c. So for derivatives, a goes in front of e. For integration, divides. So that's generally what you have. Another integral, 1 over x dx, is ln of absolute x plus c. All right, so absolute value is not here for decoration. I'll put it in blue. Must have absolute value. Absolutely critical. And the reason is the domain. Domain is the reason. If you draw 1 over x, you see that the domain is from negative infinity to 0, union 0 to infinity. If you just draw ln x without absolute value, you only have on one side, which is 0 to infinity. And that's a problem, because when you have equal in equation, you need to be allowed to plug in same numbers on both sides. So if you are to use, let's say, negative 2, well, you can, because it's just 1 over negative 2. Awesome. If you don't have absolute values, you can't use negative 2. So that's the problem. You must have absolute values. They're not there for decoration. When you have absolute values, your limit graph looks like this, covering both sides and having the asymptote at 0, but this one had asymptote at 0, so you can't plug 0 on either side. But all other numbers you can plug in. So absolute value must be there. Cool. And so we did 0, we did constant, we did x to the n, which includes your polynomials, includes obviously linear line, y equal mx plus b, or quadratic, and all of that stuff, and then other functions as radical and rational. We did e, we got the one for the ln, and now it's time to write 6 of the trig functions, and then 2 inverse trig functions, and the list is done. And again, you are supposed to know all of these except this one, because that's the only one that it's different than what you guys had so far. All right, so what are the 6 trig ones? Integral of sine x dx is negative cosine x plus c. Integral of cosine x dx is positive sine x plus c. So now the minus signs are opposite than what you had for your derivatives. Derivative of sine is cosine. Integral of sine is negative cosine. One more time. Derivative of sine is cosine. Integral of sine is negative cosine. Be careful about that. Now, what are the other basic integrals? Is integral of tangent basic? No, it's not. Because you don't have a derivative whose answer is tangent. So basic integral is secant squared x dx, whose answer is tangent x plus c. That's the basic integral. And cosecant squared x dx, that will give you negative cotangent x plus c. And the final 2 for trig, secant x tangent x dx will give you secant x plus c. And finally, cosecant x cotangent x dx will give you negative cosecant x plus c. So these are your 6 trigonometric integrals And the bottom 4 are, right, weird, so on. Now, do we have integrals of tangent and cotangent and secant and cosecant? The answer is yes. All of those integrals are going to be learned in Calc 2. Some of them you will be able to learn this semester in 5.5, but in Calc 2 they all show up, and you will see an integral of tangent is going to be ln absolute secant plus tangent, stuff like that. So it's going to be cool. Now we have a very important integral for Calc 2. You got to star this one. I mean, all of these are important for Calc 2. Integral of 1 over 1 plus x squared dx also can be written as integral of dx over 1 plus x squared, and that's the inverse tangent one, inverse tangent x plus c. Now, in many places, this integral will be a little bit different. They would say 1 over a squared plus x squared, or x squared plus a squared, whatever. X squared plus a squared, you can put them in any order, dx. And that's going to be 1 over a inverse tangent x over a plus c. That's the one you're going to see most of the time, because you are going to have 1 over x squared plus 9, 1 over x squared plus 16, or something like that. And recognizing this as inverse tangent will really save your bacon when you have to do the integrals. And I think we got everything that it's important. There are some properties and things. Just going to make sure that I didn't miss on any of these. Ooh, inverse sine. That's it. That's the last one. So, so if you have an integral of dx of 1 minus x squared is just going to be inverse sine of x plus c. So note that all of the integrals have plus c. I also gave you the 2 purple formulas. Those are going to be high frequency, right? If you have inverse tangent or something, or the e, generally you'll have the ones that have purple form rather than red form. Red form is just basic x, and this is over here 1 plus x squared. This is going to be x squared plus some number. Now there are properties, and there is a way to compute c, which we are going to tackle on Monday. All of the chapter 4 homework should be open for you to practice all of these things. And we'll finish this on Monday, and then we will vote for exam 3 for some day. Bye.